There are limits to how well our ears can differentiate between sounds occupying similar frequencies. Masking occurs when two or more sounds occupy exact the same frequencies, or more precise, the frequencies within one critical band. In this process, the signal which cannot be heard is called maski. The signal which is perceived is called the masker. To overcome masking problem, there are two ways. One way is to wait until the masker disappears, and the second is to increase the power of the masked signal. The certain level after which masked signal will be again audible is called a masking threshold. To measure the effect of masking quantitatively, the mask threshold is usually determined. The mask threshold is the sound pressure level of a test sound, usually a sinusoidal test sound, necessary to be just audible in the presence of a masker. Mask threshold, in all but a very special cases, always lies above threshold in quiet. It is identical with threshold in quiet when the frequencies of the masker and the test sound are very different. If the masker is increased steadily, there is a continuous transition between an audible or unmasked test tone and one that is totally masked. This means that besides total masking, partial masking also occurs. Partial masking reduces the loudness of a test tone but does not mask the test tone completely. This effect often takes place in conversations. Masking effects can be measured not only when masker and test sound are present simultaneously, but also when they are not simultaneous. In the latter case, the test sound has to be a short burst or sound impulse which can be presented before the masker stimulus is switched on. For data compression, the use of sound perception in critical bands and absolute threshold only is not sufficient for high compression rates. The basis for further data reduction is the masking effects investigated by Zwickler. So the idea is to use and explore the perception in critical bands and also the masking effects to be used in data compression. So the basic principle is that we have a test signal called the maski. It's placed at the center frequency of the critical bandwidth. Then we have one masking signal called the masker. And then we see that if the power of the maski is weak relative to the total power of the maskers, the test signal is not audible, so the test signal is masked. In order for the test signal to become audible, its power has to be raised to above a certain level, to above the masking threshold. Broadband noise assumes a white noise in the range from 20 Hz up to 20 kHz. Since white noise covers the whole perceived frequency range, it can hide out any sound. So in this picture here, we see the masking threshold for pure tones masked by broadband noise of different density levels. This means that if we have a white noise with density level of 10 dB, the 1 kHz pure tone has to be greater than 30 dB to be perceived. So here, for example, we see the density level of 10 dB for the white noise, and we see that is the level of the test tone is to be 30 dB to be perceived. Here we have the threshold of hearing in quiet, and then here we have in this masking thresholds for broadband noise. The spectral density of white noise is independent of frequency. It produces no pitch and no rhythm. The frequency range of white noise in auditory research is limited to the 20 to 20 kHz band. The spectral density of white noise is independent of frequency. It produces no pitch and no rhythm. The frequency range of white noise in auditory research is limited to the 20 Hz to 20 kHz band. Besides white noise, there exist noises such as pink noise, in which high frequencies are attenuated. Another important broadband noise is called the uniform masking noise. Strong frequency dependence in the spectral density of noise leads to narrow band noise and to low pass or high pass noise that we will see later. If masking effects on the slopes of such noises are sought, then care has to be taken to produce slopes of the attenuation of the noise as a function of frequency that are at least as steep as the frequency selectivity of our hearing system. Although white noise has a frequency-independent spectral density, the masked thresholds indicated by the solid lines are horizontal only at low frequencies. Above about 500 Hz, the masked thresholds rise with increasing frequency. The slope of this increase corresponds to about 10 dB per decade. At low frequencies, the masked thresholds lie about 17 dB above the given density level. Thus, numbers representing the values of spectral density indicate that even negative values of the density level produce masking. Increasing the density level by 10 dB shifts the masked threshold upwards by the same 10 dB. This interesting result indicates the linear behavior of masking produced by broadband noises. At very low and very high frequencies, masked thresholds are the same as the threshold in quiet, as we can see here and here. It is interesting to note that the strong individual differences in the dependence of threshold in quiet on frequency almost completely disappear when thresholds masked by broadband noises are measured, an effect that is based on the ear's frequency selectivity representing masker and test tone within the same band.